Question 6a. Figure 10 shows a box at rest on a table. Describe how Newton's third law applies to the box and to the table. So Newton's third law says for every force there's an equal and opposite force. So basically the box will be pushing down on the table with a certain force. The table will be pushing back up on the box with the same size force but in the opposite direction. Part B. A car of mass 3,000 kilograms travels at a constant velocity of 5 meters per second. So that's the mass, and that's the velocity. Calculate the time, so that would be t. It would take for a force of 4,500 newtons to accelerate the car to a velocity of 30. Give your answer correct to two significant figures. Select an equation from the list of equations at the end of this paper. So we're looking for an equation that's got mass, velocity, time, and force in it. Because that's just saying the force makes it accelerate, so we don't actually need that. Right, let's have a look. Has this got those things in? Nope. Has this? Yeah. Force, mass, velocity. That's just the change. That will be the velocity at the end, and that's the velocity at the start, so that's still velocity, and the time. So we can simplify that to F equals the change in the momentum. Mass times by velocity is momentum, divided by the time. So the force equals the change in the momentum, divided by the time. So we want to work out the time. Let's use the magic triangle. I've got something on the top shelf here, so that goes on the top shelf there. And then I've got two spaces and two things. Shove those things in those spaces. Now cover up what you're looking for, and what you're left with is how to work it out. So we're looking for time. Cover up time, and that is going to be the change of momentum. So delta mv. This triangle thing here means delta, Greek letter of the alphabet. It means change in. So the change in the momentum divided by the force. So the mass is 3,000 kilograms. The velocity is changing. Velocity at the end is 30. Take away the velocity at the start, which was 5. Divide that by the force. If you wanted to simplify it, it would look like that. Now that comes out as 16.6 recurrent. 66666. Now they're wanting it to two significant figures. Now a significant figure is just the first figure that is not 0. So that first figure there is a 1, so that's not 0. So that's where the significant figures kick in. So this is going to be the second significant figure. Now we need to take into account this third significant figure. Now because it's a 0.6, it rounds up the 6 here to a 7. So that's 17 to two significant figures. Now if you're wondering why I've done this bit here, it just simplifies it a little bit. What I could have done is I could have left it just as mv, take away mu divided by t, like this. So I could have just done 3,000 times by 30, take away 3,000 times by 5, and then divide all that by 4,500, and it would have still came out as 16.666. Try it, just to prove it to yourself. Last question. Question C. A car is moving at constant velocity towards a brick wall. The car collides head-on with the brick wall. Use Newton's laws to explain the forces acting on the car before and during the collision. So Newton's got 3 laws. Newton's first law, often called the law of inertia. There's a few different ways of saying it, but basically, if the forces on an object are balanced, then if the object is at rest, which means not moving, then it will stay at rest, and if it's already moving, it will continue to move with a steady speed. So how does this apply to this? So the car will be moving along at constant velocity. So before the collision, the car has a steady speed, so that must mean it's got an overall resultant force of 0. Now, if you're wondering what forces would be on the car, it's obviously a forward force from the engine, but there's also a friction force going backwards because of air resistance and because of friction between the tyres and the road. Now, Newton's second law is basically the force equals the mass times by the acceleration. In other words, if you take an object with a certain mass and place a certain force on it, you will make it accelerate by a certain amount. So Newton's second law is concerning the relationship between these 3 quantities. So when the car crashes into the wall, there's going to be a massive force acting on the car's mass, which will make the car decelerate. To a stop. Now, with regards to Newton's third law, again, there's many ways of saying it, but basically, Newton's third law is for every action, there's an equal and opposite reaction. So as the car hits the wall, there'll be a big force by the car on the wall, but there'll be an equal sized force, but in the opposite direction, by the wall acting on the car, which will damage the car. It'll make the front of the car crumble. And if you wanted to draw a picture, there's your wall. There's your car. Don't know what kind of car that is. There's one force acting that way. That's the force of the car on the wall. And that's the force of the wall on the car. Equal in size but opposite in direction. And that is enough to get your 6 marks. Right, that's that full paper finished. I hope it was helpful. If it was, can you hit the like button and subscribe to my channel, because I'll be doing a lot more of these exam papers. Thanks very much, and bye for now. Want to see more videos like this? Subscribe to my channel, GCSE Physics Explained. Thanks very much, and bye for now.